there, everyone. So this is being recorded the day before 2025 exam on this topic. And so let's do the 2024 paper. So this is Physics, Earth and Science, Earth and Space Science, 2024 NCEA 1. This is Assessment Standard 92047. We are only going to use the formula sheet that is given to you. Some of the questions here are really easy to solve actually using more advanced techniques, but we're going to use what's given to us as if we were sitting an exam. I haven't gone through these questions before, so I'm only going to use these formulae, and I'm going to use the most common calculator that students will use, the FX 98 series. All right, so with that said, let's do it to it. So the first question is energy changes. Janet drops tennis ball from the top of a building. Good for her. Described energy changes transfer that take place as the ball falls. So she's got the ball on the top of a building. Why she does that, hopefully there's no one below her. She's got the ball's going to fall. Okay, describe the energy changes. Well, at the top is gravitational potential energy, and that's going to turn into kinetic energy by the time as it falls. That's what gravity does. Gravity does work, and it transfers the potential energy into kinetic energy. That's mechanical energy, that's moving energy. The other thing we should maybe note is it's not going to be perfect. There's going to be some heat. There's going to be some sound, maybe. Probably it may kind of distort the ground a wee bit as if we hit the bottom, but it's not going to be perfect. So the potential energy is going to be slightly greater than the kinetic energy. You're going to lose a little bit. Probably not much, but it's still going to be a little bit more. All right, so the mass of the tennis ball is 0.0585 kilograms. So, okay, so it's already in SI units. That's good, and that's our mass. And the tennis ball falls through a height of 14.7 meters. So that's our change in height. Gravitational potential energy. So that's that. And we have 8.6 joules. So it's already in SI units. It loses. Show that the gravitational potential energy the ball loses as it falls to the ground is 8.6 joules. Okay, so as soon as you see gravity, you should be thinking G. And for this, G is given as 10 in SI units, so it's in newtons kilograms. All right, so let's take the formula that's given. Mg change in height. So everything is given to us. Let's put in those numbers and see if we actually get 8.6. So the mass is given as 0.0585 in SI units, so we can only put units in, times the acceleration from gravity, times the change in height, which is 14.7 meters. And we're going to grab our calculator and put those numbers in. So 0.0585 times, well, I put G there, but G is 10 times 14.7, and that's 8.8995. that's 10. And I mean, that's, if we round to one decimal place, it's going to be pretty close to 8.6, 1 dp. All right, so the next question asks us to calculate the speed, should be velocity, with which the ball hits the ground. So after it falls, it's 14.7 meters. Okay, the key insight here is to know that if we kind of ignore heat, and I can see down here that anticipate the next question, the potential energy at the top is going to be equal to the kinetic energy at the bottom minus a little bit of entropy. We already know the potential energy at the top. It was, what did I say it was? 8.5995. I'm going to put all those numbers in so we can, rather than 8.6. So we know that they're equal, so we can put in our formula for kinetic energy. So kinetic energy is given in the formula sheet as half mv squared. Next year when you do calculus and physics, you'll see where we get this half and the squared bit from. Take those, so we know what m is, we obviously know what half is. The only thing we need to find is the velocity. We don't know what that's going to be, but I mean, we can find it pretty easily now. So let's divide both sides by half to get rid of that half. Grab our calculator. Divide by 0.5. That's that, 17.199. The mass is already known. So mass is 0.0585. So let's divide that by 0.0585, and we get that. So 294. So V squared equals 294. That means that V must equal the square root of 294. So let's take the square root of that. And we get 17.15. 17.15. Are we done? No, we need to get the unit. So it's going to be 17.15 meters per second. It's not going to be exactly that velocity. It's going to be slightly less than that. We're going to lose a little bit of that potential energy in the form of heat and sound and deformation. But that's the maximum, and it's going to be pretty close to that. So, all right. So I think I've pretty much already answered this question. So the potential energy is going to be greater than the energy. It's not going to pick up energy on the way down. It's not going to be close to the speed of light or anything. So the energy, the potential energy at the top is going to be greater than the kinetic energy at the bottom. So that's one thing. And we lose a bit of energy. Well, we don't lose energy of useful energy because we can't create or destroy energy in the form of heat, sound, etc. And we do that because there's a force actor, and force really is friction or air drag. So that would be a good enough So we're never going to quite get that 17. So the velocity at the bottom, is going to be a little bit less than what we worked out. Probably not much at all less, but still a little bit less. Now we're told that Janet starts enlisting her friends on her ball dropping escapades. So her Janet's friend Maya retrieves the ball from the ground, and runs up 2 flights of stairs, covering a total height of 15 meters. So you should be having alarms go off straight away. She has a mass of 48 kilograms, and it takes her 34.2 seconds to reach the top. Are they in SI units? Well, this is in meters, this is in kilograms, this is in seconds, so they are in SI units. Always run that little test. We can't use our equations unless they're in SI units. Calculate the power. So we need power. And power is P, and it's going to be in watts. Describe the meaning of power and how it relates to Maya running up the stairs. So power is converting work or energy in a time. So it's how quickly we can do things. Something like that. Okay. State the assumptions we make. Well, we make the assumption that the assumption we make is that she goes straight up. As if she's going straight. So she's going up the stairs like that, but it's the same as if she was going from the top to the bottom like that. The assumptions we make is that she's not carrying anything else apart from the ball, so that's a good point. We maybe assume that the measurements are exact. Okay, so let's work it out. So the power is given as power is equal to. Let's use the equation that they give us. They give us this equation here, where this is change in energy is power and little t is time. Now, first thing we need to work out is the energy. So I guess the other thing we could say is that all of the energy is converted from kinetic energy to. So it's converted from potential energy to kinetic energy into potential energy. So first thing we have to work out is this change in energy. So the mass is going to be 48. And I guess we would say that we include the weight of the ball as well, 0.0585. So that's going to be 48.0585. I mean, that's a tiny, tiny amount of weight compared to her 48 kg. But I mean, if she picked up a really, really big weight, like 20 kilos, and carried that up, it would definitely affect the end result. And the change in potential energy is going to be mg, change in height again. So that's going to be 48 point, I'll put that in, times 10 for gravity times 15 meters. And it's going to be some number. It's going to be very, very similar because we're kind of like reversing the ball drop. So 48.0585, let's put that in, times 10 times 15 meters. So that's going to be 7,208.775 joules. Are we done? No. All we've done is we've got that. We've got time that's 34 point, what was it? 34.2 seconds. Now we need to find power. So using this formula here now, 7,208.775 is going to be equal to the power times 34.2 seconds. So therefore, our algebra comes into play now. It's going to be 7208.775 divided by 34.2 seconds. And now we just use our calculator. So we've got that, and we are going to divide this number here by 34.2, and we get 210.78, so 210.8, so 210.8 watt. Well, it is watt. It's watts. I put the little line there to show that it is watts. And that's what power is measured in. Quite a bit, actually. All right, so let's get to thermal energy. So Oliver wants to keep his water cool the whole day while he's at school. Why he needs to do that is beyond me. I'm just going to turn off that speaker. The whole day while he's at school, I mean, he could just use the fountain. It just keeps it cool. Firstly, he tries freezing the water to take to school. Over the day, Oliver finds it takes a long time for the ice to melt. Once the ice has melted, the water gets to room temperature quite quickly. I cover this topic really thoroughly in a previous video a couple ago. I think it's Heat Energy Explained or something like that. But before we do that, a good practice when we are in an exam is to look at what they're giving you and sort of apportion what is the letter that goes with this. Well, the specific heat capacity of water is little c. Is it in SI units? Yeah, it is. It's in joules per kilogram. The latent heat of fusion is this huge number here. What letter is that? Well, that's big L. Is it in SI units? Yes, it is. It's in joules per kilogram. Mass of the water is 750 kilograms, 0.750 kilograms, so that's little m. This one here is volume. It's not given in any of the formula, and I suspect it might just be a red herring. Okay, what does the term latent heat of fusion? So this is represented by this little formula here, ML. So this is the thermal energy required to transform 1 kilogram of a substance, in this case water, from ice
to liquid and vice versa. Okay, so if we have a 1 kilogram block of ice, we need to put this huge number here into it to transform it into water. And conversely, if we have 1 kilogram of liquid water, we need to take this amount of energy off to transform it into ice. It won't just do it all by itself for any reason. All right, so now it wants us to calculate the heat energy required to change the state from solid to liquid. So we're going to use the formula that they give us, the correct one. Do not use the that one. That's for heating the water up. This is for transforming it. So the mass is given as 0.750 kilograms. It's already an SI unit, so do not use the volume for this. We use the mass. And the L was given as this huge number here. Times... I've got the formula sheet in front of me, so I'm just using that. Okay, well, now it's just a matter of grabbing our good old calculator. Let's clear all of that. 0.750, but I mean, it doesn't matter, times this huge number, 250,500. Joules. Remember, you always need the units. Probably more likely you would say 250.5 kilojoules, to be honest. Which is a lot of energy. That's why it takes so long to thaw that ice out. And if you notice here, the latent heat of fusion is way, way greater than the specific heat. So it takes several times more energy to thaw the water than to heat the water. Which I suspect might be the next question. And it is the next question. The temperature against time graph below shows what happens to ice when ice is taken out of the freezer. So use the information provided opposite and the graph below to describe the reason why it takes a longer time for the heat to turn from the water to turn from ice to water, essentially. So on this axis here, we have the time. So it's going to be in there, and this is going to be the thermal energy. All right, so here it heats up fairly quickly here, and in here it is going to be the MC change in temperature. So this is specific heat that's working here. Then when it reaches a freezing point, 0 degrees Celsius, now it's latent heat that's doing all of the work. The latent heat is way bigger than the specific heat, so we need lots more of it from the outside air before it can melt. And then as soon as it's melted, the latent heat is irrelevant, really, and then it just keeps going up. And if you notice the slope here, the slope here is going to be the same as the slope here. And that would be the answer to that one. So some variation of what I said there would be. All right, the next question is Oliver now decides he wants to use a thermos flask that holds the same volume of water. Okay, so that's important. So we know that the volume is the same, therefore the mass is the same. So the mass is known. The thermos flask is known as a vacuum flask. Good. The double-sided glass vessel that is designed to minimize heat transfer by keeping hot things hot and cold things cold. In case you did not know how thermos flask works, describe 2 features of the thermos that reduce heat transfer. I'm going to actually do 3. So there are 3 ways that heat transfer can be minimized, and they all appear in here. So the first one is conduction. So conduction is when heat moves through solid. Okay, so the glass itself is a poor conductor. Okay, describe 2 features. The other thing which is a poor conductor is the stopper. So the stopper is probably made of some sort of rubber based something, I guess, which is also a bad heat conductor, or a poor heat conductor. All right, the next way that heat can be transferred is by convection. So here, the vacuum itself, vacuum itself is a poor conductor. It's a poor medium for transfer of heat. Okay, so heat doesn't travel across a vacuum because there are no particles to interact, and there's no kinetic energy transfer. So I do a bit on that on my previous video. The other way, which probably not a lot of students did, was radiation. So the glass is shiny, so there's a reflective coating. The reflective coating here, and that's going to reflect thermal energy. Reflecting the reflective coating will reflect thermal radiation. Radiation is, of course, transfer of heat energy through electromagnetic waves, and that's going to reflect this. It's the reason why those space blankets are effective. They reflect radiation of heat. Next question says that Oliver decides to test his thermos and finds that at the start of the day the temperature of the water is 5 degrees Celsius, and 5 hours later it's risen to 12 degrees Celsius. Show that the average rate of thermal energy absorption of the water in the thermos over the 5 hours is approximately 1.2 watts. All right, first thing we need to do is we need to work out what our variables are. So we're going to use the formula change of energy. The thermal energy is going to be MC, change in temperature. We're going to presume that it's at sea level, so it doesn't need to change states from ice to liquid water. So the latent heat energy isn't involved. It's the specific heat capacity that's involved. The mass, we know what the mass is. So the mass is what was it, 0.750 kg. We know that the specific heat capacity is given as 4,000 joules per kilogram, and the change in temperature, remember we don't really care which direction it's going, we're going to use the same amount of energy, is going to be 12 minus 5, so it's going to be 7 degrees Celsius. Okay, so we can now work out how many joules of energy goes into this water in the thermos flask to change its temperature. And for that, we're going to just grab our calculator. So our mass is 0.75 times 4,200. Let's move this calculator across. Times the change in temperature, which is 7 degrees. And we come up with 22,050 joules. Quite a bit. Okay, now we know the energy, we need to work out the power. And for that, we're going to use the formula that's given in the formula sheet. The change of energy is going to be equal to the power times the time. I've noticed last year they changed T. The year before that it was change in T, but now it's just time. So that's good. We know this. This is going to be this. The time, we kind of know this. We have to always ask ourselves, is it in SI units? And the SI unit for time is not hours, it's seconds. So we have to work out how many seconds there are in 5 hours. So 5 hours times 60 minutes times 60 seconds. So there are 18,000 seconds in 5 hours. So T equals 18,000. And now we have enough information to find the power. So let's just do the algebra first before we put the numbers in. So we're going to divide both sides by T. They're going to cancel. So the power, the average power, is going to be the change in energy divided by the time it takes. And that's going to be 22,050 joules divided by 18,000 seconds. And now we can put it in the calculator. So 22050 divided by 18,000 is 1.225. So comparing that is that, and that's going to be watts. So comparing that's going to be equal to 1.2 watts at one decimal place, or two significant figures. So yeah, it is. So a tiny little bit of energy gets through this kind of fortress of thermodynamic walls here. And I think that's the end of that question. Right, question 3 is electricity. Tana is studying the relationship between current voltage and resistance. He uses the power supply, a variable resistor, a piece of resistance wire submerged in a beaker of water. He connects the components as follows. So here is the variable resistance, the variable resistor, so you can change the the resistance. Here, of course, is the battery. I don't like how they've drawn that. It's supposed to be like that, really. And here we have the resistance wire, which I guess is a coil of some sort, which is submerged in a beaker of water. All right. And then it says in the above diagram, include an ammeter to measure the circuit current and a voltmeter to measure the voltage across the coil of wire. So here for the amp meter, we're going to put it actually in the circuit itself, in a nice clear place. So the circuit that goes through it, we're going to say is the same as the circuit that comes out. So it's going to be in the circuit. The voltmeter is going to be across this resistance wire. So somewhere between here and here, or I guess even here. Somewhere between one end of the resistance wire and the other end of the resistance wire. So we could put it here or here. It's probably the most logical place would just be straight across at the shortest possible point. And that's that. So now we're given a graph. The following graph shows the relationship between voltage and current. Using the information from the graph, calculate the resistance of the coil and include an appropriate unit. So the appropriate unit for resistance is going to be an ohm, the Greek omega. And for this, we're going to use Ohm's law. V equals IR, where V is the voltage, I is the current, and R is the resistance. And notice it's a linear relationship, so we want to find some point, which is really nice. That looks kind of like a nice point there, and that tells us that when the current is 0.5, the voltage is 4. So now we have V and I, we can find R. So let's do the algebra first. Let's divide both sides by I. They're going to cancel. So the resistance is going to be equal to the voltage divided by the current. And the voltage is 4. The current is 0.5. So the resistance is going to be 8 ohms. And that's our answer. So now it tells us to give a reason why the wire is submerged in water during the experiment. And I can think of 2 reasons off the top of my head. So first one I'd say is that it keeps the temperature constant, or relatively constant. Ohm's law breaks down when things heat up. So we want to measure the resistance of the resistance wire. We don't want to measure how hot it's going to get. So keeping it at that temperature there is going to keep it at a constant. The second reason I guess is that we know the qualities of water really, really well. So if it does heat up, we can measure it. So it's easier to measure. If you do chemistry, I think from probably next year you'll do a thing called calorimetry, which is when we submerge things in water and measure the change in the temperature of the water. But the main thing I think would probably be that it keeps the temperature relatively constant, and that way we can have we can set up our variables for our experiment really well. Next question says, using the data from the graph, what is the maximum rate of electrical potential energy being used? So let's go to our graph again. If it appears for me, there we go. And we notice here that there is kind of cutoff point here. So at that point, the current is 0.7 and the voltage is, it's this one here. So these are in increments of 0.2. So 5.2, 5.4, 5.6. So let's take that 0.7 and 5.6 and apply it. So I was 0.7 and the voltage for that was 5.6. All right, so what's a formula that links those together? How do we answer this one? Well, there is kind of a tricky word here, and it's the word that kind of you probably overlooked, and it is this word rate. When we have rate, it means with respect to time. So energy over time, and of course, that means we're going to be dealing with power. So the maximum power is going to be equal to the maximum voltage, the maximum current times the maximum voltage. Because remember, in our formula sheet, P is given as P equals IV, which is current times the voltage. So this is going to be 0.7 times 5.6. And hey presto, we grab our calculator. So the tough thing here is knowing which formula to use. So 0.7 times 5.6 is 3.92. .92 watt. Well, it is watts, which I guess we could say is roughly equal to 3.9 watts. That's our maximum amount of power that we're going to get out of that circuit, maybe before it breaks down and starts heating things up and things go crazy. Dogs start living with cats and the world goes to hell. All right, one of the components is a variable resistor. So a variable resistor, they don't show it here in the online, but a variable resistor is essentially mostly, it's kind of like a drum of rolled up, coiled up wire. So the current wants to go through here, and this is going to go probably going to go to Earth. It wants to go through here, but we kind of short circuit it, so we get like another piece of wire. If we put it there, the resistance, the current is going to go up through the wire here, and the resistance is going to be really, really low. If we put the point of contact, say here, the current has to go through all of this wire here before it can go up the current. So it's a variable resistance. So the symbol for that, the most common symbol for that I think they want you to use is that. So it's like an arrow to show that we can change the resistance. So how's the resistance used? And analyze the effect it has on both the current and the voltage. Well, it won't affect the voltage. The reason why it won't affect the voltage is that the voltage is from a battery, and the battery just gives out a constant voltage. So voltage is fixed, and we want to study the current. So really that's our kind of like the variable that we want. So if we can change this, we can move it around. So it's connected by Ohm's law. So the voltage is fixed, and we want to work out how much current we put through this resistor, we can do that by changing the resistance until we find the current that we want to put through the other resistor. So I don't know how you would write that, but voltage, it doesn't change. It can't change it. Maybe we can change the battery slightly or do something to that, but it changes the current through Ohm's law. So we want to test how much is going through that wire that's in the water container, and to do that we would change the resistance so we have the independent variable as I. And that's that. So that's the end of that exam. It's a pretty good exam, actually. It covers a lot of stuff. The big question is not so much the mathematics, it's knowing which formula to use. It really does behoove you to know the formulae and know the units. So with that, good luck everyone. I'm sure you'll do fine. And remember, physics works.